Thank you all for joining our webinar today on combination of targeted and non-targeted workflows for the identification of pollutants in river water using MetaboScape. My name is Nancy Wright-Ross, and I will be your host. If you should have any technical difficulties during the presentation, please use your chat box to communicate those issues with me. I'll do my best to help you out. Also, be sure to download the handouts for this webinar, which are also interesting and tied to this topic. At the end of the presentation, we will have time for a brief question and answer session. We ask that you use the questions box located in the drop-down panel during this time. If we are unable to get to your questions, we'll contact you offline. I would now like to introduce our presenter for this webinar, Dr. Artem Filipenko, National Applied Market Area Manager for Bruker Deltonics. Dr. Filipenko has been with Bruker for over 10 years and has over 15 years of industry experience in development of innovative methods and instrumentation for various analytical applications, including industrial, environmental, food safety, and homeland security. His area of professional expertise ranges from gamma spectroscopy and neutron detection to ion mobility and mass spectrometry. I will now turn the presentation over to you, Dr. Filipenko.
Thank you, Nancy. Hello, everyone, and thank you for joining us for this webinar. The topic of today's presentation is the use of targeted and non-targeted workflows for monitoring of water pollutants. Obviously, many pollutants are ubiquitous in surface waters because of continuous discharges from different sources. And in many cases, we do not know which pollutants and in what amounts are reaching the environment. For that reason, investigative monitoring of water bodies failing ecological standards is now a requirement in many countries, including pretty much all members of the European Union. Naturally, investigative monitoring implies a non-targeted approach to analysis, and in this webinar, we're going to discuss the combination of passive sampling technique with targeted and non-targeted workflows for monitoring of river water. So River Clun in Wales, England, is going to be our subject, so to say, and a real-life example for the day. It is currently failing to meet their ecological standards, with the main reason for it being the sewage water. Local administration started an initiative which they call Clean the River Clun, with several participants, and the key objective to restore the water quality. As you would expect, investigative analysis of water along the river was the first step in this initiative. And our collaborator, Dr. Anthony Durrell of National Resources in Wales, was leading this effort and working in close collaboration with some of my colleagues at Bruker on the data analysis side. To collect the water samples, 8 different sites have been selected along the river. The sites include locations up and downstream from the local wastewater treatment plant. On this map, the water treatment plant is located close to the center, very close to the sampling point 4 right here. The samples have been collected using a passive absorption technique and sample collectors called Chemcatchers. These samplers have been deployed at all 8 sites for 4 weeks at a time for a total duration of 10 months. So this is what this Chemcatcher sampler looks like. It's a completely passive device that can be used in almost any water environment. So it accumulates and concentrates trace levels of chemicals over the time of deployment. And it can also be used to calculate the time-weighted average concentrations of accumulated chemicals. For analysis of collected samples, a Bruker QTOF system was used, obviously. This class of instruments provides a number of very clear advantages for investigative screening. Firstly, QTOFs can acquire full scan data with much faster and with higher sensitivity than triple quad instruments. It means that when it comes to screening for more than few hundred compounds, QTOFs can outperform triple quad systems by a good margin. Secondly, QTOF instruments can capture all the data all the time, And that means that data can be analyzed even retrospectively, either for specific compounds added to the database using standards, or for suspected compounds based just on their molecular formula. And lastly, QTOFs are high-resolution systems, and they're less susceptible to space charge effects than, say, ion traps. It means that they can utilize accurate mass and isotopic pattern measurements for confident identification of analytes and be less susceptible to interferences. In a given case, the experimental setup and analytical methods were the same as in standard Bruker TargetScreener solution, and included, of course, Bruker QTOF instrument itself, Bruker Elute UHPLC running 15-minute gradient, and the standard software for data analysis and compound database. Speaking of databases, the TargetScreener database includes over 3,000 analytes. The method allows to screen for all these chemicals at once without targeting any of them specifically. Analytes in a database are referred to as known unknowns, and I know it can be a little confusing. And any compounds not listed in a database are referred as true unknowns. The method allows to detect and identify them through non-targeted screening using a workflow originally developed for metabolomics applications. This workflow allowed by Bruker MetaboScape software relies on a number of automated tools and algorithms to pick out true unknowns from the sample, extract their features such as molecular formulas, isotopic patterns, fragmentation patterns, and to identify them with high confidence. Once identified, these true unknowns can be added to the existing database to become known unknowns, and that, of course, would simplify their detection in the future. Better yet, screening for newly added known unknowns can be done retrospectively using saved data from previous analyzed samples. The mechanism that makes this retrospective screening possible is called broadband collision-induced dissociation, or broadband CID. It means that a couple times per second, QTOF instrument alternates between collecting full scan mass spectra with no fragmentation at all and collecting broadband fragmentation spectra in which all lines are fragmented indiscriminately. So this way, all information on chemical composition of the sample is collected at all times in truly non-targeted manner. Another term often used for this approach is DIA, or Data Independent Acquisition. The instrument of choice for this particular project was Bruker Impact 2. It's a high-resolution system, well suited for this kind of applications. It's a mid-level workhorse with resolution of 60,000. And on this slide, it is shown among other instruments from 2020 Bruker lineup, right here in the square. Starting from the benchtop called Compact on the left with resolution of 30,000 to Maxis 2 with resolution of 80,000. And of course, 3 different models of timsTOF instruments right here. And we will talk about them in details later in this presentation. The newest timsTOF, Flax, was introduced last year and combines conventional ion spray source with MALDI for special omics applications. As already mentioned, the TargetScreener solution is built on the Bruker QTOF technology, and the basic principles of its operation are following. So analytes from HPLC are injected into the electrospray ion source and ionized. Then ions are introduced into the vacuum through the ion funnels, guided through the isolation quadrupole and the collision chamber. So then injected into reflectron fly tube, where they separate by their mass to charge ratio based on the time it basically takes them to fly up and down. Finally, they're detected, and that gives us the mass spectrum. There is really nothing too complicated about this. Now, why high resolution and accurate mass are actually important? Well, let's take a look at this real-life example. This is a chromatogram of fungicide in a real-life matrix. we can see many peaks and do not really know which one is our target. However, we do know the nominal mass of this fungicide, in this case, is 343 Daltons, and we can extract its ion chromatogram. With a resolution of 0.1 Dalton, it will look something like this. This is what you get with typical quadrupole mass spectrometer, and you still don't really know which peak is your target because we have several. So let's increase the resolution to 10 millidaltons and extract another chromatogram for this fungicide. So now we get 2 peaks. It's better, but we still cannot be certain. So for that reason, let's increase the resolution further to 1 millidalton. And now we are in high resolution domain. So finally, we get a single peak and can see with certainty, so this is our target. And this, of course, is an obvious advantage of high resolution systems, but by far not the only one. As I mentioned earlier, when running the TargetScreener method, a broker QTOF performs 2 different experiments on each analysis cycle that repeats a few times per second. In the first experiment, the instrument collects a full spectrum of all parentymes, like so. So basically no ion isolation, no high energy collisions, and no fragmentation, just a full scan of all parentymes. In a second experiment that follows, the system accelerates all ions in a collision cell and performs broadband collision induced dissociation, or broadband CID. No ion isolation takes place, and all ions are fragmented completely indiscriminately. It means that the system collects information on all fragment ions at all times. Both measurements are done in a quarter of a second. It means that with frequency of 4 Hz, the system collects both full mass range parentyme scan and full broadband CID scan. It further means that it's quite enough to keep up with modern UHPLCs. Abundance of the generated fragmentymes provides a rich source of so-called diagnostic ions. These diagnostic ions are used for confident identification of target analytes, and obviously, more criteria you have to check, more confident you can be in your identification. So now let's review an example to get kind of a feel for how these things work in real life. So here we have 3 pesticides in one mixture. All 3 have the same molecular formula, the same exact mass, so they are isomers. In the extracted ion chromatogram, we see 4 peaks for 3 pesticides, and obviously that's kind of strange. So let's extract spectra for each one of these peaks. We'll get something like this. So the first one doesn't have expected chlorine isotopic pattern, and we know that it should be there because there is chlorine in molecular formula. So this is a totally different compound, actually a fungicide, that just happens to have the same exact mass and be present in this mixture. So that happens. The last peak we can identify as one of the target pesticides based on its retention time that matches the library. So we're good with this one. The 2 peaks in the middle, however, are very similar retention times and very similar mass spectra. There is really not that much of a difference between the 2. Which one is which is not really clear. And here, high resolution or accurate mass cannot really definitively tell them apart. However, MS analysis can. So if we look at broadband CID spectra for these 2 chromatography peaks, we see that the parentymes are the same right here, but the fragmentymes are different. So unique fragmentymes can be used to distinguish even isomeric compounds, although not always. Now we can extract ion chromatograms for these fragmentymes and perform quantitation for each one of the 2 pesticides individually. Being able to select different ions for quantitation, including fragments, for example, is very important to avoid interference in cases like this one. The data processing in TargetScreener Workflow starts with automatic calculation of exact masses for target analytes based on their molecular formulas, and this is done by the instrument automatically. Then ion chromatigrams are extracted for these exact masses. Then the system checks for presence of any peaks in the extracted ion chromatigrams, and if there is more than one peak, the system further checks the retention times and compares them with the database. If a match is found, the system checks for presence of diagnostic ions listed in the database for the given compound. Finally, the identification scoring is based on 4 criteria, namely mass accuracy, the retention time, diagnostic ions such as fragments and alternative ionization patterns, and the atopic pattern. In case of truly investigative screening, the objective can be defined as monitoring for unexpected changes and differences between different samples. Monitoring any changes from the steady-state background requires a completely non-targeted approach for both data acquisition and processing. In case of the river Clun, we were looking for any changes in the water over time and from one sampling location to another. This type of analysis is well developed and automated in metabolomics applications, and Bruker has developed very powerful software solution for that. So, MetaboScape software package, it's a complete solution for screening for true unknowns that integrates and automates data acquisition and normalization, the replication of known unknowns, identification and annotation of true unknowns, and finally, it provides statistical tools for identification of correlations and dependencies in large data sets. This is an overview of MetaboScape user interface that we're looking at here. On the top, we have task management bar. It allows to switch between different operating modes, such as compound identification, library search, and so on. Right below, we're looking at the overview screen. We have table of analyte samples, a bucket table with annotation for each one of the analytes, or buckets as we refer to them, in the selected sample. And statistical plots showing comparisons between samples on the bottom here. Identification and annotation of analytes is done with 5 different software tools. So known unknowns are automatically annotated via matching of the complete bucket table to a list of known unknowns and MS spectral library search. For true unknowns, the system automatically generates the most likely molecular formula based on an accurate mass and the true isotopic pattern for the detected analyte. Once the most likely molecular formula is automatically generated, it can be sent to a compound caller. This is another software tool that searches several online databases, such as PubChem and ChemSpider, and there are others, can be user libraries as well, to retrieve possible candidates for molecular structures. For confirmation, the structure candidates can be in-silico fragmented, and the generated fragment patterns can be compared to the SMS data acquired in experiment. Different possible hits or structures are ranked based on the match of measured and predicted fragment times. In the end, each bucket or analyte on the report table is annotated with information on what tools have been used for its identification and how confident the identification actually was. We can see the example of such annotation on the bottom here. As another example, here is a part of the bucket table after analysis of water sample from sampling point number 4 at the river Clun. For instance, entry number 39 is tramadol. It's actually a narcotic pain reliever with high risk of addiction and dependence, and obviously a prescription drug. Entry number 41 is sulfasalazine. It's an anti-inflammatory drug often used for treatment of arthritis. And another example, entry number 46, is citalopram. That's actually antidepressant sold under brand name Celexa, among others. And obviously, the table goes on. If we go further through the report, we will see that in this particular sample, the system was able to identify and name 94 analytes. And in total, the report table included over 1,400 buckets or analytes annotated to the level of molecular formula. So yeah, it's quite a cocktail of different chemicals in this river. In terms of the compound classes that the system identified, they're the following. So 3 antihistamines, 3 herbicides, 5 antibiotics, 5 antipsychotics, 12 antidepressants, 14 cardiac medications, 22 different drugs of abuse, and 27 other medications, including sleeping aids, pain suppressants, anti-inflammatory drugs, and so on. Plus, of course, over 1,000 of other molecular formulas, which are not known drugs or common chemicals. As I mentioned earlier, MetaboScape software provides very powerful tools for statistical analysis of large data sets. It also makes it very easy to compare different data sets by presence and abundances of specific analytes. For instance, here we are comparing data sets from 2 different sampling points on the river Clun and can see the relative abundances of all analytes in the bucket table. And that type of analysis allows us to extract information like this, for example. So here we're looking at the distribution of relative abundances of herbicides and fungicides by months at 2 different sampling points. So site number 4, shown in orange on this graph, is located right after the local wastewater treatment plant. And site number 2, shown in blue, is located a few miles downstream in the city. So firstly, we can notice that the abundance of herbicides and fungicides further down the stream from the wastewater treatment plant is higher. It means that they're leaching into water along the way and not coming only from the water treatment plant. Secondly, the abundance of these chemicals is the highest in August and September, which probably has something to do with the local treatment schedule. Another interesting example is the distribution of caffeine in the river water by months. Firstly, we can see that its abundance is highest right after the local wastewater treatment plant. It is in the sample collection site number 4, shown in blue. Abundance of caffeine reduces as we go downstream further from the plant. So collection site number 1 and 8 are shown in orange and gray, respectively. It means that caffeine definitely gets into the river from the local water treatment plant and can be actually used as an indication of its effectiveness. Interestingly, we can notice that abundance of caffeine grows steadily through spring months. I suppose people are waking up after the winter. And one more example, the distributions of antidepressants and antipsychotics by months. These 2 distributions are very similar and show the same pattern with abundances going up in the summertime and down in the winter. There is a very distinct and peculiar spike in December for both antidepressants and antipsychotics, and I'm afraid that might be related to the holiday season. Very sad indeed. So with that, let's summarize a little bit. The combination of passive sample collection with targeted and non-targeted workflows on a QTOF instrument is a powerful and effective method for monitoring changes in the river water pollution. TargetScreener Workflow allows rapid screening and quantitation of known unknowns using databases with more than 3,000 compounds. And MetaboScape Workflow is a very powerful tool for identification of true unknowns using embedded analysis tools and data processing algorithms. Now let's switch gears a little bit and discuss a new technology that Brooke introduced a few years ago. I'm of course talking about trapped ion mobility separation, or TIMS. Its purpose is to augment conventional QTOF analysis with additional separation dimension and help to resolve correlating isomers. So how does TIMS work? Well, different ions have different collisional cross-section, or CCS values as we call them. Like with these two sailing ships, more sails or greater collisional cross-section means stronger interaction with the wind or the gas flow. In case of TIMS, we're pushing the ions forward with the gas flow, just like the pose, while holding them back with gradient of opposing electric field. And you can see it on the diagram right here on the bottom right. In the result, ions separate and spread out along the gradient of electric field in accordance with their collisional cross-section and interaction with the gas flow. Thus, this technique gives us a very effective and controllable separation of analytes based on their gas phase mobility of their ions. So let's take a look on what's inside. This is a diagram of the TIMS cell, the gas flow, and the electric field distribution inside of it. We have a capillary inlet for the ions, an entrance funnel to focus ions along the central axis, an analyzer section with a gradient of electric field inside of it. This is where ion mobility separation actually takes place on this gradient of electric field. And finally, the exit funnel that ejects ions into the QTOF part of the instrument for further analysis. So now let's take a look at how it actually works. So the first step of the separation cycle is called accumulation. Ions are introduced into the TIMS cell through the capillary and pushed by the gas flow into the analyzer section, so something like this. There, ions face the gradient of opposing electric field and separate according to their mobilities. Note that often we use terms ion mobility and collisional cross-section almost interchangeably, since they're very closely related, of course. The second part of the separation cycle is the elution. So the gradient of the opposing electric field is reduced step by step, and trapped ions are ejected into the mass spectrometer for further analysis. Ions with greater collisional cross-section are injected first, and the most compact ions last. This gives us an ion mobility spectrum, or so-called Mobiligram. Now, Mobiligrams are not to be confused with chromatograms. These are actually two different things. So here is a real example that shows practical value of using ion mobility separation. We have a mixture of two isomeric compounds, quercetin and morin. Both of them are just food supplements. So these two compounds coelute and produce a single chromatographic peak that we can see right here. Worse yet, they both produce very similar fragment ions. So from the mixed mass-mass spectrum, right here, it is impossible to say if we have one or another or both of them together. However, with addition of TIMS, we can see two separate peaks in the Mobiligram, very clearly separated. From it, we can produce individual MS spectra for each one of these peaks and confirm that we actually have a mixture of both quercetin and morin in the same sample. Now we can actually see some unique fragments that do not overlap as much. Better yet, we can actually quantify them individually, even when they're still in the same mixture. Now let's review another example more relevant for water analysis. As you obviously know, PFOS is persistent, bioaccumulative, and very toxic pollutant. Another thing that you may or may not know is that aside from the most common linear molecular structure, PFOS actually has several isomers shown here. Presence of more than one isomer in a sample can complicate identification and accurate quantitation, since all of these isomers have the same exact mass and some of them coelute. In this experiment, we created a mixture of 4 PFOS isomers and analyzed it with HPLC timsTOF in a negative I mode. For convenience of presentation, different PFOS isomers are color-coded, so you can track them in the following slides. So here we have a base peak chromatogram of a sample with these 4 PFOS isomers mixed together. And we can extract an ion chromatogram for exact mass of PFOS. Happens to be 498.93 Daltons. And what we see in the bottom center is the limit of what we can produce with conventional HPLC QTOF. So we get 3 separated peaks for a mixture of 4 isomers. So that obviously means that at least 2 of them coelute. However, with timsTOF, it allows us to further separate these isomers by collisional cross-section values. And once we do that, as we can see on the chromatogram on the bottom right, the central peak is actually a superposition of 2 different peaks. We can also extract ion Mobiligrams for these 4 isomers, so we can see them here on the left. Notice how most of them separate from each other, although obviously some of them still overlap, those with very close collisional cross-sections. Further, we can extract mobility-filtered mass spectra that you can see on the right. And what's important here is how clean they come out without any noise or interferences. And speaking of signal-to-noise ratio, here is a comparison of PFOS and chromatograms at different concentrations. So from left to right, 0.5 nanograms per milliliter, 50 picograms per milliliter in the central column, and 25 picograms per milliliter on the right. So notice the signal-to-noise ratio in the top row. This is a performance of straight LC QTOF, basically the same instrument, but with team separation turned off. Now let's compare it with the 2 rows below. So these guys right here. These chromatograms were obtained with addition of teams filtering by collisional cross-section. The difference between teams and no teams chromatograms is quite significant, especially at low concentrations of 25 picograms per milliliter right here. What it means is that timsTOF does not only allow to separate coeluting isomers, it also improves the limits of detection and confidence of identification through better signal-to-noise ratio. And this brings us to the second summary. So TIMS offers several advantages for targeted and non-targeted workflows, namely separating isomers and isobaric compounds for screening, quantitation, and non-targeted workflows. Clean MS and MS-MS spectra are beneficial for library searches and identification of unknowns. Collisional cross-section values can be used as additional confirmation criteria. And in many cases, timsTOF can demonstrate high sensitivity due to filtering of matrix background and better signal-to-noise ratio. Well, finally, some acknowledgements. Most of the work on River Clun was done by our collaborator from National Resource of Wales, Dr. Anthony Goel. My Brooker colleague, Dr. Karsten Weisman, performed most of the data analysis. And 2 other colleagues, in particular, Andrea Kainer, provided this very interesting data on PFOS analysis with timsTOF that we just reviewed. And this brings us to the end of this presentation. Thank you for your attention, and I will be happy to take any questions.
Great, thank you, Dr. Filipenko. Yes, as he stated, we are now ready and open for questions. I know some have come through already. Your first question here is, can the chemical formula and isotopic pattern be calculated from an entered peptide sequence?
So isotopic pattern can be calculated from chemical formula, yes. And chemical formula can be obtained from the accurate mass measurement. So I guess the answer to the question is yes, if I understand the question correctly.
Okay, and if we didn't, I'm sure that they'll contact us and let us know they would like more information on that question. Next question, how hard is it to calibrate the system?
It's actually pretty easy. So the teams component, we recommend the calibration once a week. We use just a standard tune mixture. It doesn't require taking a source off or anything of that sort. The calibration is linear. There is no compound class dependencies or anything like that. And the QTOF part of the system, that's actually calibrated automatically. There is a special segment, separate segment in each injection. And either MetaboScape workflow or the TargetScreener workflow performs it automatically. So it's completely invisible to the user, but actually quite effective.
Okay, another question here. What types of libraries are available from Bruker for MetaboScape analysis?
There are actually quite a few different ones. For this type of application, probably two are most relevant. So there is Bruker HMBD metabolite library. It's Bruker developed, highly curated MS spectra as well as retention times for the analytes. And there is a third-party developed library for MetaboScape called the MetaboBase personal library. So that one contains more than 100,000 compounds.
Okay, another question. Is the BB as in boy, CID as same as auto MS?
Not really. So because auto MS typically implies isolating parent ions for further fragmentation. That means that it's kind of data-dependent acquisition, so you need to set some kind of a threshold so that system will pick the parent ion from the incoming spectrum and then kind of flag it for fragmentation on the next cycle. Broadband-CID fragments everything indiscriminately, so there is no parent ion isolation. You get all the data all the time, and that's basically its benefit and sort of a key value proposition.
Okay, another question here. What sort of statistical analysis can you do in MetaboScape?
So MetaboScape provides pretty much complete set of full standard statistical tools like PCA, ANOVA, hierarchical clustering, volcano plots, PLS, PLSD, all of that stuff. And of course, if anybody is interested in even more sophisticated analysis, it is possible to export data to third-party software as well.
Okay, let's see a question. How can we figure out the precursor and fragments on TIC if we apply bbCID to do MSMS?
Say it again?
Yep. How can we figure out the precursor and fragments on TIC if we apply bbCID to do the MSMS?
So, like I said, broadband CID is kind of indiscriminate fragmentation of everything, of all parent ions. So, strictly speaking, you're looking for a combination of parent ions and their fragments, comparing them to the database. Direct correlation in this case is not necessary.
Okay, another question. Can the measured CCS values of metabolite be used to generate analyte lists with MetaboScape?
Yep, absolutely. So it's very common, and by adding collisional cross-section values, it's actually possible to kind of improve the identification process, right? Now there will be not 4 kind of common criteria, but rather 5 for confirmation. So accurate mass, isotopic pattern, retention time, fragment times, but now also collisional cross-section can be added as additional identification and confirmation criteria.
Okay. Can I add my own library entries to the database?
Sure, of course. Actually, quite easy to do. Obviously, we recommend running standards to make sure that what you add to your library is actually what you think it is. But even if you do not have standards, you can still run what we call screening for suspects, which means that you provide system only with the formula of your suspected analyte. We do not give it any other information. And the system is still able to scan for molecular formula. It will collate it in the accurate molecular mass and provide information and it picks there, regardless of if you know what the retention time should be or not. So obviously you do not have the same accuracy of identification and the same confidence level, but you can still get information if something like it is present in your sample or not, even without having a standard handy.
Okay, well, we're about out of time. If we did not, for whatever reason, get to a question, we will definitely contact you offline. I want to thank everybody for joining us this afternoon. You will receive the recording of this webinar within 24 hours. And please be sure to also visit us online, as we are continuing to add to the tour for the virtual events at www.bruker.com. And we certainly all hope that everyone stays safe from COVID-19. And thank you so much for joining us today. Have a great rest of the day.